Now I'll hand over to Henrik.
Thank you very much. Good morning, everyone. My name is Henrik Kramselund. I'm very happy to be here, very happy to be in Budapest and see your lovely city. And I'm very happy to be at this conference for the first time. My presentation is available as a PDF and it's already on GitHub. So if you go to GitHub and use my nickname, Kramse, then you can find it using activity as a search term. So it should be possible to get this presentation immediately if you like. The presentation also has some contact information for me. I'm just a network and security consultant. I have been working with networks and security since the early 90s. I'm a huge fan of firewalls, and I would like to state that immediately because I will be making some comments about firewalls later on, but I'm a huge fan of firewalls. I run a small network, AS57860, where I try to implement some of this stuff, and I usually work from Denmark, but I also travel a lot, and I have been around the world in different places to do testing and pen testing and building networks. I also like to enjoy the RIPE conferences and be part of the community like we do at this event. And I will be around both today and tomorrow, so if you have any questions later, please approach me and ask them. So this presentation is about security on the internet. And as you may know, that when you're connecting to the internet, we immediately receive traffic from unknown sources. We are immediately getting scanned. We are seeing the noise on the internet tinnitus. It's kind of like a background noise whenever we connect to the internet. And we should, of course, try to be proactive and test our networks using active penetration testing methods. So hopefully most of you will know that it is very useful to do port scanning. It is very useful to try to look at your attack surface from the outside. And that is what this presentation is also about. So this talk will be about DDoS testing your infrastructures on the internet. I will have an ultra short firewall description. What is a firewall? Because that creates some problems for us when we do the DDoS testing, but it also creates a problem for you when you are under attack from DDoS sources. So I will be talking a little bit about doing port scans for discovery of infrastructures, because those will be the weak points that we will be attacking. Then I will follow up by some detailed advice how to perform an active DDoS simulation. So I call it a simulation, I call it a DDoS test, but I'm trying to mimic what the attackers do to our networks. But instead of having this chaotic attack on your network where you don't really know what's going on, you don't know what kind of traffic you're receiving, we try to do it in a more structured way so we can see how the devices react and then what kind of logs they log, how they actually behave during an attack. So we try to do more structured DDoS testing. So that will involve running various tools in various circumstances and with various options. And I'm trying to be very specific because a lot of these tools have many options. So I'm trying to lay out a structure and how to actually perform a minimal DDoS test, and then you can get creative afterwards. And being evilly creative sometimes is quite nice, because then you can try to protect your network from these evil attacks afterwards. And when these evil attacks come, and unfortunately, as we have seen in Denmark and other places internationally, we are getting attacked. We are getting attacked all the time. So at the end of the presentation, I will have some advice for protection, and after the question slide, my last slide I will be presenting, there's also going to be some slides which have some pointers to other references and other tools and other methods for protecting. So some of the protection part is left out because of time. These attack tools that I will be talking about is mostly some that are already developed. Some of them have been around for many years. Maybe you know them already, but I have added a few things of my own, and I have tried to update this presentation to be kind of state-of-the-art how we can do DDoS testing ourselves with a low budget. So you don't need a lot of money to perform this, but you can do it with probably some of your existing environment, and you can also protect a lot with your existing environment. So that's kind of the goal of today, to get you started on stuff that you can go home and try out, and you can improve the security of your networks. I also have some opinions about some of these things, and I don't mind telling you about my opinions. If it is my opinion, then you are free to disregard it. You may agree with me, you may not agree with me, and I'm very happy to discuss and talk about networks and packets afterwards. So approach me, please. That would be fun. Talking about the internet and DDoS, we know that it is trouble. I have taken some of the statistics from some of these reports. We see these reports quarterly, yearly, from different companies. In this case, it's the one called NetScout, where they say that we have these large attacks, we have these decreases and increases. Sometimes it goes up, sometimes it goes down. Some of these attacks are really, really big. When we see these numbers, when I see a number like 612 gigabits per second, that's more than I have into my network in Copenhagen. If I see the number 453 million packets per second, MPPS is millions of packets per second, that's more than my network can handle. When we see these, we may think that, oh no, I cannot protect from DDoS, I'm going to give up. I cannot protect from the largest attacks, so I'm not going to do anything. But actually, I think that most companies could actually do a lot with the existing environment you already have. There are some things that we can do to at least handle some of the low-level attacks. We can see what kinds of attacks we are receiving, and then we can perhaps ask our network providers, our ISPs, and some of them actually have methods for us to use and improve our network security by asking them to turn away traffic for a certain protocol, turn away traffic for a certain IP address. So in some cases, you may ask them to disregard a specific IP, black hole route a specific IP to help your existing network and the rest of the addresses to keep them alive and keep the other services alive. So there are a lot we can do, even if these attacks are very, very large. For the purpose of security and network security, we usually use firewalls, and I guess that all of you in your professional context will have a firewall. You will have a device that you call a firewall. You may have a cluster. You may have multiple firewalls, but it is some kind of collection of components. And I really love to point to different references that it's not just a single device. It is some kind of device that can filter traffic. It can pass through the firewall if it obeys some kind of local security policy, but if it does not match what is allowed in the firewall, it will get turned away, or it may get discarded, thrown on the floor. So when we have a packet coming in, we match it towards a local policy. If it matches and we allow it, we will pass it on, but if we do not allow it, we will throw it away. So that's what a firewall basically does. And the most important parts is actually the parts that it is allowing. So what is a firewall allowing? That is the thing that I would suggest that you focus on. Also, we would like to stress, and we have all of these zero trust networks and stuff going around in the industry, using the terms inside and outside may be a bit old, and we cannot trust the inside, we cannot trust the outside, we cannot really trust anything today, so we have to consider attacks from all sources inside and outside. If we go to Wikipedia, they have a very nice description saying it's a network security system. So it's not a network security device that monitors and controls incoming and outgoing network traffic based on predetermined security rules. So that is a firewall. And to me, a firewall is definitely not a single device. It's not a single bump in the wire. It's multiple devices. Looking at a firewall from a vendor, they will have a device under test, which is in the middle up here. It is a place where they can do stateful filtering, they can do screening, they can do IDS, IDP, they can do various security services, antivirus, TLS inspection, everything, antivirus, everything, they can do it in a single device. And they will optimize the device using a testing device, some kind of traffic generator. They will optimize the device for the common use case. The common use case being TCP, UDP. Stuff like that is allowed through the firewall. They would like it to run full wire speed, so if it's a 10 gigabit network card in the firewall, it should be able to pass 10 gigabits of network traffic. But can you really do all of this in a single box? Does it make sense to do all of this in a single box? It will become more complex, it will require more resources, and I really don't enjoy putting too much stress on the firewalls. Especially since they are sometimes using older CPUs, they're using older software, they have firmware which is updated as a single file, so if there's a bug in one part and you need to update, you may experience that you have problems in another part, another feature in the firewall that starts to act in another way, needs to be configured another way, or maybe some feature is going away in the new firmware. So there's a lot of problems by having a single device firewall. Looking at a firewall in the enterprise mindset, we usually have a firewall connecting us to the internet. So we will have the internet being our traffic generator. It's not everything that we want to have generated that is coming to our network, but we see a lot of traffic coming. We also have a secure LAN. Some people may consider their inside a secure LAN, but it may be a huge network with lots of devices. And usually you don't even know what you have on the inside. And then you may have some monitoring on your devices. And I highly suggest that you do more monitoring in your networks, because then you will know more about the traffic flows that you should allow, the traffic flows that earn you money, that are being used for services in production. So your infrastructure is based on multiple components and devices. In front of the firewall we have something, behind the firewall we have something, and that is something we need to secure. And we use the term defense in depth, and I really enjoy looking at all the devices, looking at all the components, and you should try to secure everything. So looking at a network drawing like this one, it's not a specific custom, it's intended as a generic network drawing of all the devices that we have from the internet going all the way to the servers at the bottom. So we have lots of different devices on the traffic flow way, on the route from the internet. And then we have all of these attacks from the internet. We have low-level attacks, we have high-level attacks, and we want to protect everything without losing functionality. And we don't want to have an administrative nightmare. So that's the next part we also must consider when we start going into this later on. What I am talking about when I say DDoS, and especially for this presentation, I'm talking about various attacks that use up some resource. So it's using up some memory space, interrupt processing, CPU processing, bandwidth, TCP state, firewall state, number of concurrent sessions. Anything that can use up a resource is a denial of service. When we talk about a distributed denial of service, it's multiple sources on the internet. But in this case, in our structured testing, we use a single device usually to produce this traffic. And of course, we can start spoofing lots of sources so it would look like a real distributed denial of service. But a denial of service is anything that uses up resources, and resources are limited. They are always limited. There will be bottlenecks in your network, and the goal is to configure your systems so you have as few bottlenecks and they are as high as possible so you can produce a lot of production traffic. Looking at the firewalls just quickly, this is the traffic processing on an SRX series from Juniper. It's just an example of a network device that you can buy. It has this per packet stuff that happens on the left. Then it matches a session. Usually we do stateful filtering. Then it goes to the small flow on the right bottom, or it goes through the long one at the top where it goes through a lot of different steps. So this is what happens for each packet received on an SRX firewall. And as you can see, there's lots of different parts, and I'm not going to go into details, but this is what must happen for each packet going in, going through, going out of this type of firewall. And you could find similar ones from the other firewall vendors. This is just what I happen to use usually, so I know this one better. Looking at these firewalls, we also know that they usually have a control plane and a data plane. They will typically, in the higher speed versions, have some hardware supporting the usual and the common case. So the data plane will be hardware which is designed and optimized for some use case. Then we will have a control plane, which will be the configuration stuff. You will log into the control plane, you will change the configuration, you will push these changes into the FPGAs, into the networking chips, the routing chips, everything that goes on in the data plane. If something happens to go all the way up to the control plane, it will be handled by a CPU process, so that will be limited in what the CPU can do. Whereas the data plane usually will do things in hardware and actually can perform a lot of stuff in hardware in modern devices, even the ones that I buy for my company, which are the smallest devices mostly for 10 gigabit routing. Typically also when we have a network, we will have what is called a link net and a hosting network. So we will have the services that you publish to the internet on the production network, the hosting network, in my case, and then you will have a link net connecting the devices. This link net could also get attacked, so I recommend that you do port scanning and discovery and testing on these devices too. Typically, they would be a very small network, like a /28, 26, and then the hosting network where you have your services will be a /24 or /22,000 addresses if you have them. And then we have the similar ones in IPv6, and it is recommended to have a small link network, and then you would probably have a /48 for IPv6 for the hosting parts. And you can get that from RIPE, you can get provider independent addresses, so we can move them between ISPs, and you can have multiple ISPs, and I recommend that you get IPv6 provider independent PI addresses immediately. Start applying for that through a LII, local internet registry. Since you are security people at this conference, I guess you know Nmap, the port scanner, so I'm going to go through very quickly the parts that I recommend you do before the testing. You will use a port scanner, and that will show which ports are open. The ports that are open are, of course, the ones that we want to hack. These are the ones that will create state in the devices all the way to the servers. You would, in the best case, have something that you can ping, and then you would have a TCP port and then a UDP port, some kind of service that runs on TCP, some kind of service that runs on UDP. So that would be the baseline for doing this testing. And then I would recommend doing some monitoring, make sure that you have nice green graphs showing that there are no service problems. Everything is green, everything is ready for the testing. If you have an unstable service, it's not nice to test, but if you have a green all the way 100% uptime for the last week, and you start attacking, and you see that this breaks, then you know that it was the testing that made it break. I usually use Nmap to do the port scan, and then afterwards, when I have found these services to attack, I will use the tools like Hping3 and T50 and Penguin Ping. And Penguin Ping is my own script, which is a small add-on which I have released for this conference because I was going here. I put it public on my GitHub. I put the web page up with some text and descriptions. And Hping3, T50 are on Kali already, and you can very quickly and easily install DPDK data plane development kit from Intel originally, but is now open source. And then you could run Penguin Ping on top of a Kali or a Debian. Then, using these tools, I would go through all the scenarios that I usually see on the internet being DDoS attacks. So that would be SYN flooding, it would be UDP flooding, ICMP flooding, all of these flooding attacks. I would go through all the scenarios. I would register all the changes to the devices in the network, and I would expect things to break. And usually when we do this breakage, it will be different scenarios breaking in different networks depending on the devices and their configuration. But afterwards, we will investigate, and that's not part of the presentation today, but you should investigate, is this scenario something that could hurt our network? Is it something we can turn away so it doesn't affect our network if somebody tried to attack it? And usually, you will be able to remove at least some of these use cases without losing functionality. The problem with all these tools, the Nmap, Hping, T50, is that they have a lot of options. So which options should you use for these testing, structured testing? A small hint, I usually save the IP addresses in a variable on the shell. So if I'm on a command line, I usually do this from the command line. I will save the IP addresses in a variable, because then if I mistype the variable, nothing bad happens. If you type the IP address in the middle of the night and you mistype an IP address, you are performing a DDoS on somebody else. So better save the IP addresses as a variable, and then you can use this in your Nmap command, and you can use it later on in the Hping3 and T50 and so on. So a small hint to avoid attacking other people on the internet. We don't want to do this. I want you to use this for good stuff. Then I also have a small other hint, which is to add the last line where we have the date. So having a date separated with the hping command, and then using the time in front of the hping, that will make sure that if you do a log of all the commands during the night, you will hping3 with a Control-C. It will see how many minutes, how many seconds you ran the command. So doing a complete log of your command line and have date timestamped when you started an attack and for how long you ran an attack. And you can match that up with your logs afterwards, making sure that your logs are, of course, timestamped too with the correct time. My goal when I do this Nmap is to enumerate all the ports that are allowed through the network. I will save all these files. I will output it into an IPv4, IPv6. I will making sure that I can find something to attack. Doing the port scan part should not break anything. If you have stuff that breaks and dies, then it is vulnerable to normal traffic. So that would be something to fix first. That's really bad if something breaks because of an Nmap. Then I would also do some operating system detection. I would also like to do service scanning, and one of the services that I usually find on customer routers, the ones from the ISPs, is the SNMP protocol, which allows me sometimes to see that a router in a customer network has been up for more than 700 days. So if a device has been up for more than 700 days, what is the firmware? Is that a recent firmware on that device, or is it definitely going to have some bugs? And definitely there is some bugs. In this case, it's a Cisco device, and a Cisco device that hasn't been updated for 2 years or more is definitely vulnerable to something. So that's also things that come out of this testing. When you start to investigate your network, you will see different things that you can also fix before doing the DDoS testing and before somebody attacks your network. Then moving on to these packet generators, this Hping3 is very flexible, it's very nice, it can increase and decrease the speed, which is very important when you start to see things breaking, because you want to know what broke, which device broke. So you don't want to run it with full 10 gigabit network speed, you want to run it perhaps with 1 gigabit, 2 gigabit, see where it breaks, run 1 million of packets per second, run 2 millions of packets per second, and see when stuff starts to break. And sometimes when we run these, we also monitor the devices and see if the CPU load goes to 50%. If we load it with 1 million packets per second, then would it break if we put it onto 2 million? Probably, and when we put it on 2 million, we see it go close to 100%, and then we know kind of the rate of attack which will break this network, these devices, these specific devices. So Hping3 is a very nice tool, and usually you can produce 1 million packets per second from a single process, and you can run multiple processes on your Kali Linux. Usually our machines today have multiple CPU cores. So Hping3 is a nice tool, has a lot of different options. The one called T50 has the same options and can produce the same attacks, but it also has a specialized protocol T50 option, which is very nasty because then it starts to send all protocols sequentially. So a firewall that is optimized for TCP, UDP, ICMP, receiving all sorts of protocols, all sorts of traffic, makes it go into all of these cases and special cases, putting some of the load into the CPU is really, really bad. I can tell you that when I start using this command, usually the firewall will start to break and will get overloaded, especially if you do it at a high speed in millions of packets per second. Then we have the Penguin Ping packet generator. I found a library called libmoon, which is part of Moongen, which is a packet generator based on the DPDK from Intel originally. It's now open source. Using this tool, I can write Lua scripts, and these Lua scripts allow me to re-implement in about 230 lines of Lua code the same options as Hping3. The difference is where a single process could run like 1 million packets per second, a single CPU core with this tool using Moongen can produce 14.8 million packets per second, which is the full 10G wire speed from a single CPU core on a small device with a cheap network card. So that's really, really fast, and it also has a nice option -R, so we can ask how much to generate. So the process using these tools would be to monitor the network, attack, break, and repeat. So we would start out small with small attacks, see how the network reacts, see how far the packets get into the network. They pass the first router from the ISP, they hit the firewall will get loaded a bit, we will see how it handles different kinds of traffic, and then usually it will start to break at some point. And I advise you to go through all of these scenarios first. Do not make changes during the testing because you may optimize for one use case and then later on for another use case, which may affect the previous use cases. So better to go through all of the scenarios, mark down the ones that failed, try to fix those, and then do a retest on another night. And usually I do it during night to avoid production issues. This is the command to run the Hping3. As you can see, I have exported the custom IP as a variable so I can use it further down in the tools. I am using the date command to get the nice timestamp. I have the time command, which summarizes the time. I only ran this attack for 1 minute and 7 seconds. I was very impatient that day, just trying to produce some output for this presentation. And this is the way that I start out by doing a SYN attack, SYN flooding attack on port 80, which is of course one of the common ports. So port 80, HTTP, would be a common TCP port to attack. And this is very nice because you can run this multiple times. At the end of this command, up here we have the ampersand, which means this runs in the background. So I can just use my arrow up and enter, arrow up and enter, arrow up and enter, and start perhaps 5 or 4, 6, 7, even perhaps 8 if I have a new CPU. So I can put a lot of load on the network and it's very flexible. It can do just about anything. You can control any part of the packet using the Hping3 tool. My recommendation is to run each test for at least 5 minutes or even 15 minutes. A lot of these attacks require some build-up. If you have a timeout in a firewall, for instance, Juniper SRX at one point had 1800 seconds timeout for UDP sessions. So if you created a UDP session, it would take 1800 seconds without any traffic for it to time out. So if we ran a short attack, it might be able to handle the burst. But if we wait for some more time, it may be that this table of UDP sessions ran out of space, and then it would not be able to accept any more UDP sessions on that device. So this is why I run this for up to 15 minutes. If we don't have any change, that's nice, then it's a pass. But any changing response is a result. So if you have a higher latency, stuff answers slower. If you have probes that are lost, that's a result. If you have loss of connectivity to the device, that's a result. And sometimes you have to monitor all the devices to see if there's a change. If there's a change, then I recommend that you stop the attack, see everything go green, and then retest using the same parameters to see if it really is this attack that breaks it. And then you can confirm approximately the level where it breaks, and you can try to turn it up a bit, turn it down a bit, see where the approximate level is. And that becomes important because after you have tried to make changes, then you can perhaps run with a much higher level. So we have seen in some use cases and some scenarios that we have improved the level several 100%. At one point I had a firewall at a customer. It was vulnerable to 50,000 packets per second. 50,000 packets per second is something that I could probably produce on my phone using 4G networks. So it's a very small attack size. And afterwards, they could handle millions of packets per second with the same scenario. So it becomes important when you want to demonstrate that you have improved your environment. Yes, I think I have said everything here. These are the basic tests that I recommend that you do. They are implemented in all the tools. This would be a basic test. So that would actually go through a lot of different variants of the attacks that we see on the internet. We do it structured, so we do it one by one, but an attacker would probably mix up these. They would send a burst of this and a burst of that, or even mix it at the same time. And of course, after doing these sequentially, it would make sense to try to do them mixed. And if you can mix it all up in a random fashion and your network still survives, that's a good thing. So using my tools, Hping3 or the Penguin Ping, with these options, then you would be able to do these SYN, SYNAC, ICMP, UDP flooding, and it is quite easy to perform this. Usually when I run these tests, I use the tool IFPPS to show the interface packets per second on my device as I'm sending the traffic, so I can see how much am I sending, but you can also monitor your local switch, your local router. All of these routing devices, switching devices have methods for monitoring a port, seeing how much traffic you are sending and how much traffic you're receiving. Usually I would also tune this test, making sure that I not always run with the full speed, because we want to find out which devices break, and then we can turn it up to flooding at the end. So don't start out by flooding everything, because then it will just break. It's more interesting to see when it breaks and see what kind of thing in the device breaks. Is it because of the interrupt handling? Is it because of these state tables? Is it something that we can actually fix or improve by the configuration? So don't just turn it up to flooding, even though it's quite fun to flood stuff. Using the Hping3 and the DDoS testing tools, I would also advise that you try to attack some of the network devices, the router. Usually a router could have something like the secure shell running, should not be open to the whole internet. So by demonstrating that you can make it break or make it high load, high CPU load, then you can ask people to turn it off afterwards using something like router protection filters. It's something that should be implemented on all routers servicing your network. So only the ISP can log into that router using SSH. And if it's running BGP, the routing protocol, that's actually a TCP service running on 179. And you can also try to attack that one. And we have seen networks coming offline because we attack the router in front of the network. So it's not only your part, the part that you control, but you must ask your ISP to also improve their network a bit. And it is called router protection filters. I told in the title for this that IPv6 testing is also part of this, and my favorite tools have not supported IPv6, and I'm a very fond of IPv6. I did my thesis in Copenhagen 20 years ago about IPv6. Nobody uses IPv6 in Denmark, but I would like to test using IPv6. And since these tools did not support IPv6, but these tools were open source, I could actually take the Hping3 tool, then I could put it on GitHub, I could replace all the references to IPv4 with IPv6, and I actually, even though I'm a bad programmer, I could actually do a version that supported IPv6. But even better, the new tool that I have created, the script that I created on top of this Moongen, uses Lua, and it already implements IPv6. So now I can use a small script in Lua. I can modify and customize this script, and that is my preferred way of doing IPv6 testing. And basically the testing process is the same. The main difference is that we cannot do an Nmap full scan of a network because subnets in IPv6 are quite large. So it is required to look into the firewall configuration, the server configuration, and see which ports are open to find the open ports. Maybe it's within the first 100 IPs if it's statically allocated, but when you have the services and the ports available, then you can definitely use these tools. Either the old Hping from 2018 that I created, which is kind of a bad, just replaced all the references to IPv4 with IPv6, but it's much better to use this Moongen from this person, Henrik P. from GitHub. There's also some other test cases. Usually I don't spoof my source. Usually it's very nice to see in the logs that we have a specific IP address scanning us, testing us, DOSing us. We can look into the logs, find my IP and see what goes on, but definitely you want to try spoofing, and it is implemented in all these tools that I have told you about. There's also nice evil features like this one, which is about fragmenting packets. So if you have a fragment of a packet, then the firewall device, the secure devices, they have to wait for the rest of the fragments. And guess what? These tools do not send the rest of the fragments. So the firewall will spend time keeping and storing these fragments until they time out. So again, some of these features built into the tools are very nice for breaking the devices. If we start to attack a network and have the monitoring running, we can see there's a large green line at the start, and then it starts to break. This is from a tool called Spoofing, which I really enjoy because it does multiple probes, and then it records the results in color. So the color blue on the first one here says that it's losing some probes, 1, 2, 3 probes, and then it gets even worse because the color changes, so it loses more probes. And usually you would be sending 20 probes per minute and seeing which ones that are not responded to. When we go further on in this case and this test, we see that it goes into red. Being red means that the service is definitely offline. It has 19 to 20 probes lost, so there's no service on this service that is being tested. And that is what the customers of this web shop or production site, production service would see. We can go on and retry the test, so we see a small green part after 11, and then we retest and see that it really indeed goes bad with this scenario. So in this case, it was a spoofing attack, and it also worked. And as I remember, I spoofed the IP addresses of the network itself, which should not come from the internet. So maybe look into the configuration and do not allow your IPs to be the source of traffic from the internet. That seems bad. So turn that traffic away. Using the tools that I have mentioned already, we can do a maximum speed test. We can do the full 10 gigabit and 14.8 million packets per second. That is actually the maximum number of packets with the minimal size on a 10 gigabit connection. So it's not as much about the bandwidth handling, because usually these firewalls can handle large packets, data transfers, but if you try to send the smallest packets, it goes bad. Because every packet must go through this long flow of traffic, all the packet steps within the devices. So handling 14, 15 million packets per second is really, really hard in the device. So usually they will sell you a device that cannot handle this, but they will handle some kind of iMix, some kind of mixed traffic with large packets. These modern CPUs that we have for many years support methods for sending and receiving high speed. Using this Lua, it is using Lua JIT, which is just-in-time compiled, making it a small loop, which can run very efficiently in our modern CPUs. The modern CPUs are connected with the network cards using, for instance, this data plane development kit. It was originally from Intel, so most of the cards supported are from Intel, but there are also other vendors and other cards supported by this, and it is open source, so you can buy 1 gig cards, 10 gig cards, 40 gig cards, and you probably shouldn't try to buy 100 gig cards and produce packet DDoS testing traffic. I would rather have a number of smaller cards and maybe a switch to aggregate. So if you wanted to produce, say, 100 gigabits full capacity, then you would have a switch with 100 gig and then 10G or 40G, and then send the traffic and then allow the switch to aggregate it into a full 100 gigabit. And that would certainly be possible by just having perhaps 10 machines or fewer. I'm using a very small device, and this is not a recommendation of Dell. It just happens to be the device that I could get for pretty cheap. It's not very big. I can travel with it. I have it in my hotel room. I set up this small testing environment with a small 10G switch, and it's just any modern new CPU would probably work. Then you would look into having a PCI x8 slot, and then I use an old Intel card, which is something you can find on eBay pretty cheaply. Using the tool that I have used on top of this, Moongen allows me to produce, as we can see in this case, 14.8 million packets per second, which is not full 10G, so it's only 7.6. So looking at a graph, you may think that, oh, my device can handle 10G, but it is actually not 10G in bandwidth, but it's 10G in packets per second. This tool can be used for UDP, ICMP. It can be used for just about any protocol you wish because it's written in Lua. There's a lot of Lua scripting implemented already. You could add your own protocol. I have messed with this, and again, I'm not a great programmer, but very, very quickly you can start to generate whatever kind of traffic you want, and you can actually create it in full wire speed mode. I'm just going to go a little bit quicker. Just saying that this is comparable to real DDoS. It's very, very approximate to what I have seen in real life networks that I have been running. And I see lots of different results from this. And the results is that we should do more packet filtering. So my recommendation is to look at all your devices from the internet all the way to your servers. Looking at these devices, we can actually do specific stuff at specific points, and a lot of it can happen in hardware. So looking at a router, it can do stateless filtering of individual packets. So if you know that there are some protocols that you're not using, you can turn it away by the router. If you want to shape and do some distribution, you want to allocate a specific bandwidth number for a specific protocol, you can do that in your routers and switches. Then we can see the security services, security devices, what you usually would call a firewall, would handle less traffic. And that is actually the goal of the protection that I'm advising. Start to use the features already available. And I can see my time has run out now, but I'm just going to quickly point you to these slides where I have taken a design approach saying that for some protocols we may need full 10G, but for some other protocols we will need less. So if we need less, why do we allow more into the network? And by going further, we can look into the specific ports that are available. We can look into the configuration statements. This is from Junos, where I have limited ICMP to 100 megabit because nobody wants 10G of ICMP traffic into their network. So better turn it away before it reaches the firewall device, which needs to handle it in all of these steps that we already have seen. And UDP 1 gigabit, because usually we don't have more than a few hundred megabits, depending on your use case and your network. Some networks use file transfer using UDP, and they will definitely need more. But in a common network, you can use configuration statements like these, and you can find them for your own devices in your own network. And if we do this, we can see that kind of like, in this case, a 3.5 gigabit network attack, and it resulted in only 350 megabits being sent on to a 1 gigabit firewall. I will unfortunately have to stop now. Time has run out. So before I get dragged off, I will be here for today and tomorrow. Very happy to answer questions. Go to GitHub, find the presentation if you like. And thank you very much for allowing me to talk about this subject.
Thank you, Henrik. Thank you very much.